For most of the 20th century, scientists believed they had the universe figured out. After the Big Bang, space was expanding, yes, but gravity, the great cosmic glue, was expected to slow it all down. Over billions of years, the pull of all that matter should have gradually tamed the expansion, maybe even brought it to a stop. That was the accepted story. Until 1998, when everything changed. Two independent teams of astronomers set out to measure how fast the universe was expanding. They studied a special kind of exploding star called a Type 1a supernova, a brilliant detonation that always shines with nearly the same brightness. Because of that uniform glow, these stellar explosions act like cosmic mile markers. By comparing how bright or dim they appear from Earth, astronomers can tell exactly how far away they are and how fast the universe has stretched since their light first began its journey. But when the data came back, the universe refused to behave. Those distant supernovae were dimmer than expected, meaning they were farther away than their redshift implied. Somehow, the expansion of the universe wasn't slowing down at all. It was speeding up. The discovery hit the scientific world like a thunderclap. Gravity was losing. Something unseen was overpowering it, a mysterious, repulsive energy pushing galaxies apart faster and faster. Overnight, cosmology was rewritten. The universe wasn't just expanding, it was accelerating, and the cause of that acceleration was given a name that sounded more like science fiction than science: dark energy. The deeper astronomers looked, the stranger the picture became. Calculations showed that all the stars, planets, gas, and dust, everything we can see, make up less than 5% of the total universe. About a quarter is something equally mysterious called dark matter, which holds galaxies together with its unseen gravity. And the rest? The remaining 70% of everything that exists, the dominant force of the cosmos, is dark energy. It's everywhere, woven through the vacuum of space itself. You can't see it, can't touch it, can't measure it directly, yet it dictates the fate of galaxies and the ultimate destiny of the universe. That means most of reality is invisible, and the part we know, the glittering stars, the cosmic fireworks, even life itself is just a small ripple in a vast ocean of the unknown. To make sense of this invisible energy, scientists turned to history, to Einstein's equations of general relativity. When Einstein first formulated his theory of gravity in 1917, the prevailing belief was that the universe was static, unchanging. His equations, however, predicted a universe that should be expanding or contracting. To counter that, Einstein introduced a special term, the cosmological constant, denoted by the Greek letter lambda. It represented a uniform energy filling all of space, balancing gravity's pull to keep the cosmos static. Later, when Hubble discovered the universe was expanding, Einstein scrapped his constant, calling it his biggest blunder. Ironically, that so-called blunder might be the key to understanding dark energy. If space itself possesses a small but constant energy density, an intrinsic push built into the fabric of reality that could explain why the expansion is accelerating. The cosmological constant would be Einstein's vacuum energy, silently driving galaxies apart across the cosmic void. But there's a problem, a huge one. According to quantum mechanics, even empty space isn't truly empty. It's filled with virtual particles that appear and vanish every fraction of a second. Each of these quantum fluctuations adds a bit of energy to the vacuum. When physicists calculate how much energy this would create, the result overshoots the observed value of dark energy by a factor of 10 to the power of 120. A number so enormous, it's been called the most embarrassing mismatch in the history of physics. Something in our understanding is catastrophically off. Either quantum theory needs rewriting, or dark energy isn't just vacuum energy, it's something else entirely. If the expansion is truly accelerating, what happens next? The implications are chilling. Right now, we can still see distant galaxies, their light stretched and reddened by cosmic expansion. But as acceleration continues, those galaxies will move away faster and faster until their light can no longer reach us. One by one, they'll fade beyond the cosmic horizon, leaving our night sky emptier with every passing eon. In the far future, The Milky Way and its neighboring galaxies will remain bound together by gravity, but everything else will vanish from view. The universe will grow colder, darker, and lonelier. Stars will burn out. New stars will stop forming. The cosmos will enter a long, dim twilight, an age when only black holes remain, slowly evaporating into nothing. We might be living in a brief, extraordinary moment, a time when the universe is still young enough to see its grandeur. Billions of years from now, the evidence of this cosmic story will be gone. The universe will still exist, but its past will be hidden, erased by expansion itself. But what if dark energy isn't constant? What if it's something that changes something, alive, dynamic, and unpredictable? Some physicists believe dark energy isn't just a number in Einstein's equations, but a field, a cosmic substance that evolves over time. They call it quintessence, borrowing the ancient word for the fifth element, beyond earth, air, fire, and water. Unlike the cosmological constant, quintessence isn't fixed. It can grow stronger or weaker, shifting as the universe expands, influencing how galaxies drift apart. If that's true, then dark energy might not be eternal. It could eventually fade away, allowing gravity to take over once more, or, in a darker scenario, it could intensify until it consumes everything. That leads us to one of the most terrifying possibilities in all of cosmology: phantom energy. Imagine an energy so powerful that it doesn't just push galaxies away, it rips them apart. In a phantom energy universe, the expansion rate doesn't just increase, it accelerates uncontrollably. Every second, space stretches faster than the second before. At first, only the most distant galaxies drift away. Then, over billions of years, the pull becomes stronger. The gravitational bonds holding clusters of galaxies together begin to snap. Next, it tears apart individual galaxies, the Milky Way, Andromeda, all of them unraveling their stars into the void. But it doesn't stop there. As the expansion reaches smaller and smaller scales, solar systems fall apart. Planets are torn from their stars. Eventually, even atoms can't hold together. The electromagnetic forces binding electrons to nuclei fail. Everything, down to the most fundamental building blocks of matter, is ripped apart in an ultimate cosmic disintegration. Physicists call it the Big Rip, and according to some models, it could happen tens of billions of years from now if phantom energy exists. But that's the thing. We don't know if it does. We barely understand what dark energy is now, let alone what it could become. All we know is that it's real, and it's changing the destiny of the cosmos. There's another, more radical idea. Maybe dark energy doesn't exist at all. Maybe what we're seeing, the acceleration, is a sign that Einstein's theory of gravity breaks down on cosmic scales. Some researchers think that general relativity, though immensely successful, might not tell the whole story. If gravity behaves differently at vast distances, that could mimic the effects of dark energy without actually needing it. The challenge is that testing these theories is incredibly difficult. We can't experiment with galaxies in a lab. All we can do is observe, measure, and compare, hoping to find clues in the faint light of distant stars and galaxies, echoes of the past that might reveal the universe's hidden laws. If gravity itself needs rewriting, it would be one of the most profound revolutions in science, on par with Einstein's own discovery a century ago. For now, dark energy remains the greatest mystery in modern physics. We don't know where it came from, what it's made of, or what it's ultimately doing to our universe. It could be a property of empty space, a relic field from the early universe, or even a hint of higher dimensions bleeding into our reality. And yet, in that uncertainty, lies something deeply human. Our species has existed for barely a blink of cosmic time, on a tiny planet orbiting a mediocre star. And still, we dare to look into the abyss and ask, what is driving all of this? We build telescopes that can see billions of light years away, not to escape our smallness, but to understand it. Every discovery, from dark matter to dark energy, reminds us that the universe is stranger and more magnificent than we can imagine. If the universe keeps accelerating forever, then the script of existence is already written and it ends in silence. With every passing billion years, galaxies will drift farther apart, their light stretched thinner and dimmer until even the nearest cosmic neighbors fade beyond the horizon of visibility. One by one, the brilliant clusters that once painted the universe will disappear, leaving our night sky dark and lonely. The Milky Way, once surrounded by countless companions, will stand isolated in an endless sea of black. In 1 trillion years, even the stars within our galaxy will exhaust their fuel. The skies will be stripped of starlight, no suns, no planets, no warmth. What remains will be the silent glow of dying embers, white dwarfs cooling into black dwarfs, their light fading into memory. The cosmos will enter what physicists call the degenerate era, when the universe is ruled not by life and energy, but by the quiet reign of decay. Black holes will become the final rulers of existence, ancient, massive, and patient. For eons, they'll devour what remains, pulling in dust, gas, and the frozen corpses of forgotten stars. But even they are not eternal. Through the slow and steady process of Hawking radiation, they'll begin to evaporate, releasing their energy back into the void, particle by particle, until nothing remains. The last black hole will fade away in a final whisper, leaving behind a universe that is still expanding, but completely dark. What will exist then? Only the faintest traces of few cold photons, drifting endlessly through the emptiness. No galaxies, no light, no sound, just space itself, stretching thinner and colder, driven by a mysterious force that refuses to rest. Dark energy will keep pushing, expanding nothing into more nothing, an infinite canvas of emptiness growing larger with every passing moment. But that's only one possible ending. If dark energy isn't constant, if it changes, weakens, or grows unstable, the story could end very differently. Some theories suggest that if dark energy reverses, the universe could collapse in on itself in a final big crunch, where every galaxy, star, and atom is crushed back into an unimaginably dense singularity. Others predict a more violent fate, a big rip. In that nightmare scenario, dark energy grows stronger over time, tearing apart galaxies, then stars, then planets, and finally, the very atoms that make up existence. Space itself would be ripped open as reality unravels from within. These possibilities might sound distant, but in the grand timeline of the cosmos, they're inevitable, the final verses of a song that began with the Big Bang. Whether the universe freezes, collapses, or tears apart, one truth remains. Dark energy isn't just shaping the stars. It's shaping the ultimate fate of everything that exists, from galaxies to atoms, from time itself to the boundaries of what can ever be known. And maybe, when everything else has vanished, dark energy will still be there, invisible, unstoppable, quietly stretching the remains of creation into the infinite dark. The universe began with light, but it may end with silence. When we look at the night sky, we see beauty, order, and light. But behind that beauty hides something deeper, an invisible power, silent and unstoppable. Dark energy doesn't roar like a supernova or blaze like a galaxy. It whispers. It hides in the vacuum, bending the future in ways we can barely comprehend. It's a reminder that the universe isn't built to be understood easily. It's built to be explored, questioned, and feared, a cosmic riddle where every answer leads to 10 new mysteries. And maybe that's what makes it beautiful. Because even if we never fully grasp what dark energy is, the search for it connects us to the deepest truth of all, that we are small, but we are curious. We are fragile, but we ask big questions. And somewhere, between the galaxies and the void, between matter and mystery, lies the story of everything we've ever been and everything we will ever be.